Stereoisomers are isomers with the same structural formula but they have different spatial arrangements of their atoms. Stereoisomerism can be divided into two categories, which is the diastromers and enantiomers. Examples of diastromers are molecules with two or more chiral centers. So for this one, it is not included in our syllabus. And the other one is the cis-trans isomer, also known as geometrical isomer. The essential requirements for a molecule to exhibit as cis-trans isomerism are it must have a restricted rotation. Okay, the restricted rotation of carbon are in the carbon-carbon double bond in alkenes or carbon-carbon single bond in cyclic compound, which is the cycloalkanes. Each carbon atom of a site of restricted rotation must bonded to two different atoms or group of atoms. For example, here we have an alkene compound. The carbon-carbon restricted rotation are on the carbon-carbon double bond. So each carbon-carbon restricted rotation, which is this carbon and this carbon, must bonded to two different atoms or group of atoms. So since these two carbon-carbon restricted rotation are bonded to two different atoms and group of atoms, so it can exhibit as cis-trans isomer. In a cycloalkane, okay, at least two carbon on the ring, okay, our cyclic compound must bonded to two different atom or group of atom, regardless where the carbon it is. Okay, so at least a cyclic compound, our cyclic compound got two carbon that bonded to two different atom or group of atom. It can exhibit as cis-trans isomers. Cis isomer is when the two groups are on the same side, like this structure. Okay, so this alkene compound got hydrogen on the same side. So this one is the cis isomer. Okay, so to draw the trans isomer, right? So first we are going to draw the carbon-carbon double bond. Right, so we have the carbon-carbon double bond and take out the another bonding, another two single bond. Okay, so like this, and then just copy back our atoms here. All right, so we have bromine, hydrogen, and now I'm going to change the position of hydrogen and chlorine on this carbon. So I'll put the hydrogen and chlorine here. So when the atoms, okay, are not on the same side, okay, like this, it is called a trans isomer. So this is the trans isomer for this structure. Okay, so same goes to our cyclic compound. Okay, when the two atoms are placed on the same side, okay, this is a cis isomer. Okay, so to draw the trans isomer, all right, so I'm going to copy back my cyclic compound. Okay, so for the cyclic compound, we have to draw it on plane. Okay, just like it be on the plane. Okay, so take out the two bonding up and down, right? And then same like before, I'll just stick to the same atom, all right? For this carbon, Br, okay? And then the next carbon, I'm going to change the position of the chlorine and hydrogen. So when the two atoms are bonded not on the same side like this, okay, so it is a trans isomer. So let's try this example. Which of the following compounds can exist as pairs of cis-trans isomers? Draw each cis-trans pair. So let's have a look at the first compound. Okay, so we have compound A, right? So we have compound A. So first, let's check whether this compound got carbon-carbon restricted rotation. So if you can see here, we have the carbon-carbon double bond. So this carbon-carbon double bond is the carbon-carbon restricted rotation. And then we have to check the second requirement. Okay, each carbon-carbon restricted rotation must bonded to two different atom or group of atom. So this is a condensed structure. So in condensed structure, it's quite difficult to check whether our carbon-carbon restricted rotation is bonded to two different atom or not. Okay, so in order to check whether this compound fulfill all the requirements for its exhibit as cis-trans. Okay, so let's label our carbon here, right? So 1, 2, 3. So we have 3 carbon, and then take out the carbon-carbon double bond. So this is our carbon-carbon double bond, where our carbon-carbon double bond here is carbon number 1 and carbon number 2. Okay, so now let's focus on carbon number 1 and carbon number 2. So at carbon number 1, we have 2 hydrogen, right? So we have 2 hydrogen, and here carbon number 2. Okay, so take out the bonding. So carbon must have 4 bonding. So since we already have the double bond here, so the other 2 bonding, we wrote it like this. Okay, so on carbon number 2, we have 1 hydrogen, okay, CH, and another one is the CH3. Okay, so CH3. So yes, it got the carbon-carbon restricted rotation, which is the carbon-carbon double bond, but then only carbon number 2 bonded to 2 different atom or group of atom. But then carbon number 1, right? So we have same atom bonded to it. So this compound cannot exhibit as cis-trans. Alright, so for the second compound, okay, so yes, it has the carbon-carbon restricted rotation. So let's open up the structure. Okay, so we have 1, 2, 3 carbon. Okay, so label our carbon and then take out the carbon-carbon double bond. Right, so this is our carbon-carbon double bond, and take out these 2 bonding. Right, so label our carbon-carbon double bond. So our carbon-carbon double bond is on carbon number 1 and carbon number 2. Right, so now at carbon number 1, so we have 2 CH2 group attached to it. So we have 2 not CH2, 2 CH3 group. Okay, so the methyl group CH3 group attached to it. And then for the second carbon, we have 1 hydrogen and another one is CH3. So even though it has the carbon-carbon restricted rotation, but then at carbon number 1, it got 2 different atoms. So no, it's not fulfill the 2 requirements. Okay, so this compound cannot exhibit as cis-trans, even though the second carbon here is fulfill the requirements, because our both carbon-carbon restricted rotation must bonded to different atom or group of atoms. For the third compound, yeah, so yes, it has a carbon-carbon restricted rotation. So as usual, let's label our carbon. So 1, 2, 3, 4, 5. Okay, take out the carbon-carbon double bond. Right, so we have carbon-carbon double bond, and take out also the 2 bonding here like this. Okay, so and then label our carbon. So our carbon-carbon double bond is on carbon number 2 and carbon number 3. Okay, so on carbon number 2, here we have 1 hydrogen and 1 CH3 group, which is our carbon number 1. Okay, and then on carbon number 3, we have 1 hydrogen and another one is CH2, right? CH3. Okay, so beware, okay, this carbon number 3 is bonded to carbon number 4, which is CH2. Okay, so jangan salah Okay, so jangan buat this carbon number 3 bonded to carbon number 5. So that's why I asked you to label your carbon. Okay, so when the 2 atoms are the same, okay, side by side like this, okay, so it means that it is a cis isomer. Okay, so this one is a cis isomer. Okay, so before that, okay, so it has a carbon-carbon restricted rotation, and also at this carbon and this carbon, the carbon-carbon restricted rotation is bonded to 2 different atoms or group of atoms. Okay, so that's why this compound can exhibit as cis-trans. Okay, can exhibit as cis-trans. Right, so the cis isomer is when the atoms, the 2 atoms are the same on the both side. Okay, so this lari macam ni. This one, kiri ada H, kanan ni pun H. Okay, so dia sama. So when the 2 side are the same, so it is a cis isomer. So to draw this trans isomer, so we have the carbon-carbon double bond. Okay, so kita draw balik. Okay, just draw this structure, and then okay, just copy the third on the third carbon. Okay, copy je balik, just copy back the third carbon. So we have CH3CH2, we have hydrogen. But then for the second carbon, we are going to flip it. Okay, so we have CH3 and then H. So when the atoms here on the both side, okay, dia tak sama macam ni. Okay, the atoms on the both side tak ada yang sama macam ni. So this one is our trans isomer. Okay. Compound D, so it got a carbon-carbon restricted rotation, but since this carbon got two methyl group attached to it, the same thing, so this compound cannot exhibit as cis-trans. Okay, for compound E, so we have carbon-carbon restricted rotation, and then at this carbon we have hydrogen and chlorine, so two different atoms. The next carbon is also got hydrogen and chlorine, so yes, it can exhibit as cis-trans. Okay, so now let's draw the cis-trans isomer for compound E. So label our carbon. So 1, 2, it's only got 2 carbon, right? So take out the carbon-carbon double bond, C double bond C, and then take out the 2 bonding like this. Okay, so the first carbon got 1 hydrogen and 1 chlorine. Second carbon also got 1 hydrogen and 1 chlorine. So when the both sides are the same atom, we got the same atom here. Alright, so this one is the cis isomer. Okay, so the trans isomer for this structure is C double bond C, take out the 2 bonding, and then just copy back the first carbon. So we have H and Cl. Okay, so for the next carbon, the carbon number 2 here, we are going to flip it. Okay, Cl and H. So when the both sides are not the same atom, so this one is gonna be our trans isomer. For the last compound here, so we got the carbon-carbon restricted rotation, which is the carbon-carbon double bond, and each carbon is bonded to 2 different atoms or group of atoms. So yes, it can exhibit as cis-trans. So to draw our cis-trans isomer for this compound, okay, so let's label our carbon. So we have only 2 carbon, right? So take out the carbon-carbon double bond, and then take out the 2 bonding like this, and then in the first carbon, we have 1 hydrogen and 1 bromine. The second carbon, we have 1 hydrogen and 1 chlorine. So since the hydrogen is the same on the both side, so this one is our cis isomer. Okay, so for the trans isomer, alright, so let's take out this skeleton first and then copy back our first carbon, H and Br. For the second carbon, flip it, right? So we have Cl and H. So this is our trans isomer.